everyone, I'm Gigi and this is my partner.
Hi, I'm Shirley. Welcome to our channel Miracle of Maths. Many people think that mathematics is very difficult and something that make their life in trouble.
Therefore, our channel will like to discuss some mathematics problem in easy and interesting way. But you can learn mathematics after watching our video. Today we are going to talk about the case study of the predator-prey model between lynx and hare.
Before we start solving our case study, we must know the modeling process. This is because modeling process is very important in solving the case study. Modeling process consists of 5 steps. First, we need to identify the problem. Then, we must formulate a mathematical model. After obtaining mathematical solutions, we need to interpret the mathematical solutions. And the final step is verifying the mathematical solutions.
Now, let us start our case study. First, we need to identify the real problem. How the lynx and hare interact, thereby affecting each other's population by prey-predator interaction. The model will be deterministic since it will depend entirely on the input factor, such as what is the natural growth rate of the hare in the absence of predation of lynx. What is the death rate per encounter of hare due to predation of lynx? What is the natural death rate of lynx in the absence of food, that is, hare? What is the efficiency of lynx to predate? After that, we need to suppose the data available as follows.
Second, we need to formulate a mathematical model. Before that, we need to do some assumptions. We assume that the predator species is totally dependent on the prey species as its only food supply. Second, the prey species has an unlimited food supply and no threat to its growth other than the specific predator. Suppose S is the size of the prey population at time t. If there were no predator, this implies that the prey species grow exponentially, and we would have S prime t is equal to xa. But there are predators which must account for a negative component in the prey growth rate. Suppose y is the size of the predator populations at time t.
Here are the crucial assumptions for completing the model. First, the rate at which predators encounter prey is jointly proportional to the size of two populations. Second, a fixed proportion of encounters lead to the death of the prey. This assumption leads to the conclusion that the negative component of the prey growth rate is proportional to the product xy of the population size.
Now, we consider the predator populations. If there were no food supplies, the population would die out at a rate proportional to its size. We will have, but there is a food supply, the prey. The energy supports growth of the predator population is proportional to that of prey. This discussion leads to the Lotka-Volterra predator-prey models, where A, B, C, and D are positive constants.
The third step is obtaining the mathematical solution. We need to solve the ordinary differential equation to find the steady state. We need to let the x priority and y priority equal to 0. From this equation, we will get the steady state at the point 0, 0 and c over d and over b. The stability of the fixed point at the origin can be determined by performing a linearization using partial derivative. The Jacobian matrix of the predator-prey model is calculated to find the eigenvalue of the steady state.
The fourth step is interpret the mathematical solutions. From the previous solutions and the given value, A equal to 1, B equal to 0.2, C equal to 0.2, and D equal to 0.01. We get the steady state at the point 0, 0 and 25. At 0, 0, the eigenvalues are 1 and negative 0.2. So, the phase portrait is unstable stable point. At 25, the eigenvalue are square root 5 over 5i and negative square root 5 over 5i. So the phase portrait is stable center.
Next, we use the mathematical software to plot the phase portrait. You can use either the MATLAB, Mathematica, or the XXPAUT to plot this. From the phase portrait, we observe that the number of pre and predator are oscillating around the steady state point 25.
The final step is compare our case study with reality. First, our mathematical result is accepted since the population of pre are always larger than the populations of predator in normal case. Second, all the results can involve one species of pre with one species of predators, so a lot of assumptions are taken. The overall conclusions, the population of prey and predator will be persistent to maintain the ecosystem if there are no other influences.
So here is around the end of our video. We hope that you will be more clear and understand the predator-prey model. If you still got any interesting topic and would like to discuss with us, feel free to comment below. Thank you for watching our YouTube channel. Remember to like, comment, share, and subscribe to our YouTube channel. See you next time!